Thank you, Tiana, for the invitation. This is a topic that I really enjoy sharing with you all. And like Tiana said, this is not only my work, but I'm trying to share as much information as I have gathered in my now 18 years of research in this topic. So I think, okay, so we're gonna talk again about bitter pit. And this is just a symptom, the way we see it. And you probably have heard of different ways that we call this symptom, depending on the variety, depending on the species. But mainly, bitter pit is allocated to apples. You all have probably seen this in Honeycrisp, but it also happens in many other varieties. We have seen other cork spot is a kind of like a bitter pit in pears, but we call it cork spot because of the symptom that develops in pear. And also some of us believe that this is also the same problem that we have in WA 38 called the green spot. It's just another way of showing up the symptomatology. And this is a cellular deficiency. And I was just hearing a talk by Dan Donaway from Cornell that he was speaking an hour ago in another meeting that is very true, and I will quote him. Sometimes when we talk about calcium deficiency, we need to be very clear, especially for all of you growers, that the deficiency is not a lack of calcium or a deficiency of supply. And I'm gonna go into that topic now, of course, in more depth. This is a deficiency that happens at a cellular level. So I'm gonna show here, this is the symptomatology that we are more familiar with, and you can see that what is happening actually in the cellular wall is that the membrane that holds the cells together becomes leaky and it breaks, and that's what's become for us visually as a bitter pit or a oxidation and a necrosis of the tissue. So these are the main conditions that will lead into that symptom that we see in the cell walls. Now, why it's so complicated is because calcium not only has that role of structure that keep the cells together. So that role that we call the structure is where calcium is binding this, what I draw here in red is the middle lamella that holds the cells together, but also calcium is here around the membrane of the cells, which is another form of calcium that I will explain in the next slide what it does. But in the structural role is where we see that it fails, especially in some more susceptible varieties, and creates this leakiness and bitter pit. Now, the second role, also being related to calcium, to bitter pit development, especially later in the season, is this role of calcium in the cell membrane, which is some available calcium that is kind of floating in outside the cells and is reactive to signals. What it means is that when we have a problem like heat stress, light, shade deficiency, insect damage, or any environmental impact into the fruit, the calcium is a signaling element that goes from the cell membranes inside the cell to make a reaction. And so that's why we call it a signaling element. Now, once the reaction is done, for example, having chios or having a thicker layer or having a protein development, for example, then the calcium needs to go back into the vacuoles and it becomes non-mobile, non-active. When this process happens later and we don't have enough calcium available, this soluble calcium, we can also create reduce or deficiency of calcium in the cells, and it could also lead to that leakiness and the development of bitter pit. So those two roles are related to bitter pit development. Now, this in a way, explain why when we evaluate calcium or total calcium in the fruit, we not always see a good correlation with bitter pit. And that's because we are evaluating all these forms of calcium, including the calcium that is not actively or important for us for the cell wall. So that's why total calcium is not a very good indicator. Okay, so what we want to do here, or I want to do here, is to show in what stage we can do or we can manage this calcium availability in that cell level. So first of all, we need to understand how it works in a normal process. Start from the soil, whatever calcium we have available in the soil is taken up by the roots, especially the root tips, and is moved up into the plant by the xylem. And this is very important to understand because that means that calcium is not a very mobile element inside the plant. Xylem also only goes upwards, not like phloem that goes both ways. And it has a limitation when the fruit matures. I'm going to explain that later. And so it's driven by transpiration and by the capacity of the xylem to move and sustain. That is a capacity of exchange capacity, similar to what we see in the soils. Another key point in this is that when we are developing that cell wall and that membranes, this happens earlier in the season when we have the cell division. It doesn't happen later, because later what happens in the fruit while it matures is that the cells start to enlarge. So increase in size, but not increase in volume, in numbers of cells. So we don't create more cells later in the season. So this is the stage that has been mentioned many times in the past by researchers. This is the time that we have to target available calcium in the soil, adequate root health and growth, and avoid a competition in that transpiration. What really causes this is really this multifactorial. And that's why it's so complicated. In the same talk that I mentioned before, Dan Donaway, they measured 45 different factors. And they found that 25 factors are actually impacting bitter pit development. So that's why it's so complicated. But at the end, what is happening, we know that is a genetical factor. That's why we have varieties that are more susceptible than others, and especially related to the longevity of that xylem that is bringing that calcium into the fruit. And the reduced ability of that membrane that I show in the signaling portion to retain that calcium. So it's a genetical component that is mostly related to this stage, what I mentioned before, not to the root growth. It's more related to that transpiration and movement of the calcium into the fruit. This is just to show the same, where it started in the 90s. That was the first thought of this xylem functionality, but then it was proven in 2004 by this researcher that that was the cause in apples. And this is just to show this Catarina is a susceptible variety similar to Honeycrisp. And you can see that in 40 days after full bloom, the xylem start reducing the functionality compared to a Fuji that in their location is not susceptible to bitter pit. And we have proven, we have seen this over and over. Licalcid has also shown some staining and differences between Gala and Honeycrisp. So this seems to be the main factor. What happened also is that while we cannot put calcium into the fruit, later in the stage, those after 40 days after, what happened, we still can gain other nutrients, especially nitrogen, potassium, and magnesium, because those elements are mobile and they can go into the plant and the fruit through the phloem. So we can still increase the level of these elements, and thus we can change the balance nitrogen to calcium. So what can we do to mitigate this problem that is genetic? We're probably not going to solve it completely in a susceptible variety, but there are some things that we can focus on. So I divide this in 4 stages: in the soil, the roots, the transport to the fruit, and at the cellular level later in the maturity. So in the soil, we have to secure that we have levels above 4. Normally, I will show a chart of the levels that we have found in Washington, but with this amount in the soil, we have sufficient to supply what the plant needs to grow. Now, in a very sandy soil like this one in this image, it's very easy to supply that if we have good irrigation that doesn't leach the calcium down. But it's very easy to supply because we can put it there when the roots are growing, and it's just a matter of adding the fertilizer that is needed, like, for example, calcium gypsum, which also provides sulfate, which are normally low in sandy soils too. So just keep up with the calcium requirements in the soil. Also, we have to focus on the balance with other nutrients, because we know that if we have too much potassium, magnesium, or even ammonium, those can compete with the uptake of calcium if they are in large quantity, especially for potassium. And we know that there are many soils here in Washington with high levels above this number here, which seems to be adequate for honeycrisp. And the pH, of course, above 8.5, we can start having some, we have enough calcium, but not necessarily available, but also it's not ideal for general root growth. So if we keep this up, we should be fine in terms of calcium availability. In a more clay type of soil where we have maybe sand in the top, but then we have a layer that is preventing adequate drainage, like Tiana mentioned before, that can prevent the health of the roots. So that's also a problem we have to be focusing on. Look in the profile of your soils and avoid those stages of excessive water and lack of oxygen, because that will prevent root growth. Now, this is very simple to show that in the soil, if we do have root hairs, the movement of calcium into the plant is passive. That means it doesn't require energy and is very fast and effective. So the movement from the soil, which the calcium normally is around the clay layers, will move with water into the root hairs. So those are 2 components that are fundamental. Early in the season, again, we need to have adequate root growth and health, but also we have to have moisture, because otherwise calcium doesn't go into the plant. This is a chart of more than 260 soils that I've been working on in collaboration with growers, where we have the levels of calcium. In white is the level that I consider adequate. So you can see how much above this level is. All of these orchards are above adequate levels. These ones here are normally associated to very sandy soils, but this area probably is easier to manage in terms of you can add calcium quite easily in the soil. But this overlay that I put here is the levels of potassium that we have in our soil. So when we have adequate levels, this range of very adequate levels of calcium, when we overlay the potassium levels, this red line is the maximum level of potassium we should aim. So all the soils here that you see that are above this line are preventing the uptake of calcium. And that's where we have to focus, not in adding more calcium, but just to control that levels of potassium that we have in our soils. So this, I kind of listed the priority, what I will be doing. So first of all, for those areas that are low in both, in potassium, like here, but low in calcium, it's easier to just supply what is needed, and you can rely on the tables that we have provided in our webpage of adequate levels of potassium and calcium. But second, I will focus on those areas that we have excessive potassium, which are everything that is above this red line, those orchards that, especially those that are in adequate levels of calcium, but levels of above 500 is way too much and probably this is preventing the uptake of calcium. And third, we have to think about this area here where we have very high levels, above 15 normally. This means in most cases that the soil has calcium carbonate. And probably this relates to high pH and the layer of caliche in the soil. And also in many cases, we have lack of drainage because of that caliche. And so the problem there is more related to that lack of drainage and infiltration of water rather than nutrients. So if we think about, we solve the problem in calcium availability in the soil, we have to focus on the root growth. And this is important because calcium is passively going into the plant only we have root tips. When the roots develop this layer here, kind of in light blue, that's a Casparian layer that prevents the entry of calcium into the xylem, which is down here. So only through the root tip that doesn't have that layer, the calcium goes there very easy and very freely. So if we don't have that root tips that you see early in the season, we don't have that passive uptake of calcium. While other nutrients like nitrogen and potassium can be taken up by not only the root tips, but the more mature section of the roots throughout the season. And we need to consider that because sometimes we don't have root tips, for example, in the middle of the summer, but we are irrigating, we are overhead cooling, we are putting water, and the plant is uptaking potassium and nitrogen together with that water. And so we can create that imbalance while we no longer have taken up calcium because we don't have root tips, but also we don't create more cells at that stage. This is to show, and this is important, of course, this vary between location, but it's very standard that in most cases, the root growth starts right after we have shoot growth. So the first shoot growth, you see in the top here, this is shoot growth and fruit growth rate. Both start before we have actually root growth. And that's because they rely in the reserves from previous year. So I draw here the line where in this chart below, we see that the root growth start growing after we start that process of cell division. So the earlier we have that root growth, we will have more supply, but initially, actually, the plant relies on whatever is in the plant as a reserve, especially for nitrogen, excuse me. This is a trial that we did in collaboration with STEMILT and Washington State funding support, where we are evaluating what can we do to improve or accelerate root growth. And so we've been trying different, maybe not very practical measures, but we have a black tarp. This is a plastic, non-permeable cover, a control, and extend day to see if we can manage that temperature. And we indeed changed the temperature quite a bit, especially early in the season. We were able to improve and accelerate that root growth with the clear plastic in the root zone, while with extend day, it was actually delayed. This might not be a bad thing, especially in very hot years, because in our case, we are working with M9, which is actually susceptible to high temperatures in the soil. But in any case, our trial was to evaluate if we were able to improve root growth and see what that impacted in terms of the plant. And I'm not going to show all the results because I have a lot of other things I want to show, but overall we observed, but only on 1 year, this was in 2018, that the clear also reduced the levels of bitter pit only at harvest, and we have no difference between the storage and the control. But there was something there. So we are continue to evaluate higher temperatures in the soil can help us to improve that root growth early in the season, because we do believe that it could be a limiting factor, especially in cold years. Okay, so we have adequate levels of calcium supply. Then we provide good root growth and healthy roots. So the third stage, and this is probably the most relevant one because it relates to that xylem timing that we have to put that calcium into the plant, relates to the movement of calcium from the roots to the fruit and to that fruit in development, fruit in cell division. So remember, xylem is one direction, is bringing the calcium into the fruit, driven especially by transpiration. So early in the season, we do have transpiration from the fruit, but later when the fruit is developing the cell wax and all that, the fruit no longer transpire. So we have a window of opportunity to have calcium into the fruit. There's also other research that show that the seeds from the fruit is a driving force of calcium to get into the fruit, which makes sense because at the beginning, we have to think, and this is the second theory that moves between concentration, that early in the season, when we don't have leaves or big leaves transpiring, how does it move? And we don't have root growth early when the cell division starts. So how does it move? The other theory from Vanguard in '79 shows that it moves from a differential of concentration from high to low concentration. So there's two forces that are taking the calcium into the fruit. Now, that's why there's a couple of research that show that early thinning can prevent the uptake of calcium into the fruit and have increased levels of bitter pit if we thin too early. That has other consequences too. So what we have to do, and this is probably where we have more tools to manage. We need to manage vigor in our orchards. We have seen that the most related condition that is related to bitter pit in Washington is the excessive vigor. So we have to manage crop load. Vigor and crop load go together. I cannot separate those two. Shoot to fruit ratio, the same. When we have too much vigor, we have reduced number of seeds early in the season, so that can prevent the uptake of calcium. We have more GA coming from the shoot growth, and GA is known to inhibit the uptake of calcium into the fruit, and also will create more shade that also have led to bitter pit. And we know that we will have more nitrogen, potassium demand with high shoot growth, and that can lead also to oversized fruit, also leading to bitter pit. So all these factors that I see that they all relate to vigor is the way I feel that we need to manage bitter pit in our orchard. I want to show here some of the factors that are related to vigor. For example, you all know that the B9, this is a work from Terence Robinson in New York. B9, this is a lower vigor rootstock, has lower levels of bitter pit compared to, for example, a G41 that have higher levels of bitter pit, right? And that's the same for the rest of the rootstock. In general, a dwarfing rootstock has less bitter pit compared to a more vigorous rootstock. The same was shown by Licalcid in his work with Nadia Valverde. They also show that more dwarfing rootstock, M9 and B9, have less bitter pit compared to a more vigorous rootstock. And the same with Musaki's work, a more vigorous rootstock, more bitter pit. So that's we will learn more about the rootstock influence, but that's pretty much very standard. In terms of nitrogen management, we also know, and this is Cosmic and Hannes from my data in my lab, and this is for more references, but we can see that the demand of nitrogen and calcium and most of the nutrients in Gala, which is known to be less susceptible to bitter pit, is higher compared to a Honeycrisp. In general, Honeycrisp doesn't like to have high levels of nitrogen. So these are the standards we should be following for in terms of demand for honeycrisp is lower than a more a less susceptible variety. According to Cheng, in 2021, he mentioned also that the foliar values for honeycrisp should be lower compared to a standard. So between 2 and 2.2 and 1 in terms of potassium, 1 and 1.3, slightly lower than what we use for the other varieties. Another point that he made that I think is very important is that we need to collect the samples before we see this typical honeycrisp chlorosis, which is, it will be a little bit earlier than other varieties. Crop load, we see that there is a relation. It's not a very strong relation in most cases, but there is a relation where, especially when we are in the very low crop load level. If we are in this very low crop load, below the 3 fruit per trunk cross-sectional area, we see that we increase the levels of bitter pit. And this has also been proven by leak acids here. Dan Donaweb show also that application of PGR, which is inhibiting GAs and growth, improve or reduce the levels of bitter pit when applied at pink. And that, of course, that relates to reducing the vigor of the shoots. Another work, and we are copying this here in Washington in a new project, is the application of apogee later in post-harvest. This author, Amarantes et al. From Brazil, they show that they reduce bitter pit levels with this application of apogee later in the season prior to harvest. I'm going fast because I have 1 minute. I have to stop. So that's in the process of cell division where the fruit start to grow. And so this is the 4th stage, which is what happened after when we no longer can put calcium into the fruit. And because there's no more cell division, no more cell development, so what we have to prevent? In this case, we think that the fruit enlargement, we have to prevent that oversized fruit, and we have to prevent the uptake of nitrogen, potassium, and magnesium because they continue going into the fruit via phloem. Oversized fruit, we know that, you growers know that about honeycrisp is very big. But we also have to prevent the stress because the stress can lead to bitter pit. And ripening is another process. During ripening, naturally, the plant needs to reduce the level of calcium to become good for the seed development. That's not our goal, but calcium levels will reduce in the ripening process as a natural process. Okay, so this is another PGR, and this is thinking about the later stage to prevent stress, where these authors have shown, the Freitas, also from Brazil, the same group, they show that in red chief is a susceptible variety with bitter pit, they reduce with the application of ABA later in the season. We are copying this too. We are trying to evaluate this later application of ABA in honeycrisp to see if we can reduce the levels of bitter pit. And in this case, they show also the increase in the ratio of potassium, magnesium in the control compared to an ABA treated. This is my work. You are the first ones to see this now. I'm going to present it next week in the Washington Research Commission review that we did see in one of the 2 trials that we are evaluating, that the ABA later in the season, pre-harvest, did reduce bitter pit levels at harvest and in storage. Okay, so with that, I'm finishing just overall message to start with the soil to secure these levels of above 4. It should not be a complicated task to prevent the antagonism with potassium in particular. promote root health and moisture and temperature early in the season, prevent the excessive vigor. This is key. This is fundamental in our region because we have a lot of potential for growing shoots. We have the best conditions to grow trees here in Washington. So this could become a problem actually for this disorder. And finally, prevent or do everything that you can to prevent stress conditions.
Great. Thank you very much. Let's give her a big round of applause. And we have some questions.